Hello, nice to meet you. My name is Takeshi Kuwada. I work for iASYS Technology Solutions for business development in Japan. I worked with a customer from a major Japanese vehicle maker to create a test data management system that is used in vehicle development. And yes, this system uses graph database. We have been creating and operating the system together with our customer for the past 10 years. We have overcome the challenges by thinking about various ideas together with our customer. Today, I will talk about that system and how the graph can help vehicle development. So let me start by telling you briefly about our customer and our company. The customer is a senior expert engineer in the powertrain, and he has a bird's eye view of the vehicle development. On the other hand, we are a global system integrator with a development base in India. We specialize in test automation systems, and our vision is to empower engineers with the advanced digital technology. What the customer wants to achieve was open test data to many engineers. What does it mean? I will explain the background in more detail. When developing a vehicle, OEM does a lot of tests. For example, the power output test to know the acceleration speed, durability test to know whether it will not be damaged after many years, noise test to know whether the noise is not too strong for drivers, and emission test to know whether the exhaust gas follows regulations. And the power data, durability data, noise data, and emission data taken in these tests are very variable because they show the performance of the vehicle itself. This data is used by various engineers. It's not just about measuring data and deciding whether it's okay or not. For example, there is a simulation engineer who calculates performance based on this data. Simple example, you can use the test data of the engine to simulate the performance of the vehicle. It is also used for various decision making. When designing a car, engineers make trade-offs between improvement of fuel efficiency and acceleration. And the data is used in this process. Also, comparing the trend data for the past many years, engineers evaluate the design. It also provides training data to AI, such as machine learning. These use cases need various data and are implemented at different levels, like system level of a vehicle or at subsystem level of a powertrain and a battery. In this way, test data is originally used by many people. However, in many organizations, it is stored in a way that is very difficult to use. Why is that? Why does such a variable data stay hidden away from engineers? The reason is that vehicle development is a very complicated process with many groups and people working together. So, let me tell you about one example, the case of a typical vehicle maker. They sell vehicles to various countries such as USA, Europe, China, India, and Japan. There are about 20 models for worldwide, including SUVs, sedans, and sports cars. Each model will be remodeled in 5 or 6 years. At the time of remodeling, development is divided into various phases from the concept phase to pre-mass production phase. In each phase, functions are designed and validation tests are performed using simulations and prototypes to meet the needs of customers. In addition, the development team is divided into groups for subsystems such as engine, battery, motor, and chassis. And among them, validation is performed on various evaluation parameters such as performance, durability, emissions, and noise vibration. And yes, the test is performed in various forms such as a simulation test, a component unit test, and an actual vehicle test. As you can see, in vehicle development, many types of information are used in a complex combination. In addition, there are so many departments and groups in the company, and so many people are involved to make one vehicle. Digital twin is one of the solutions. But the solution to map such a complicated process into digital space is not easy. There are following challenges to achieve that. Silo data. Here, test data is stored in personal computers or file server of each group. And it is very difficult for engineers in other groups to navigate data. Multiple and vendor lock-in file format. I think it is very inconvenient, but some test data are stored in various formats depending on the measurement tool vendors. In many cases, engineers can't open file without a dedicated tool. So even if you can find test data, you may not be able to open file because software is not installed on your computer. Process changes for EV development. Conventional engine-based vehicle consists of hardware parts mainly. On the other hand, modern electric vehicles consist of systems, which is a combination of software and hardware. So digital infrastructure should support both modern EV development and conventional engine vehicle development. Database integration. The company has various existing systems such as PLM and EBOM in which development information is registered. The system needs to work with them to integrate the data. Automation of data import. Honestly speaking, I'm very tired of manual data import. I think most of the test engineers feel the same way. Therefore, it is very important to reduce effort for data import. If you don't overcome this, data will be not stored. AI and analyst tool integration. It is necessary to integrate with engineering tools such as simulation software, AI, BI, and so on. Test data is valuable when used in this software. Computing power for big data. Typically, test data is time series multipoint data. Also in data science, there are many calculations which is heavy load for the computer, such as deep learning and statistical analysis. Therefore, strong computer power is required for big data use cases. Others. There are some other small challenges. So, the digital twin of the vehicle development is not an easy task. A vehicle is probably one of the most complex products in the world. However, it is very interesting to achieve the digital twin of the vehicle development. We want to provide test data to all engineers because customers want to make a vehicle with a small manpower. And the price competition of electric vehicles is very severe. We want to automate vehicle development by digital technology. Moreover, in EV development, it is necessary to use simulation aggressively. Engineers want to share data efficiently between the test department and the simulation department. On the other hand, the number of engineers who work for traditional engine is decreasing year by year. It is difficult to maintain quality with a human-dependent process. By using the knowledge database, you may be able to lower the skill set required for work and create a sustainable environment where many people can work. Furthermore, by using data science, such as machine learning, there is a great possibility that development efficiency will be improved drastically. How do we do that when we need to deal with many variety of data and this data is always organized in more silos? We must store test data in a format that is easy for everyone to find. Engineers should be able to search the data and understand what it means. Our BRICS PVM solution faces these challenges. We face this challenge with the graph database and a global standard called ASAM ODS. Also, we are lucky to work with our best partner who has a great experience in vehicle development. Now let's see how the graph helps the product development. We have mapped the development process to graph database. Here is a diagram of BRICS PVM data model. This diagram shows node and relationships in a graph database. The model is classified into 6 groups. First group, a business group that contains information such as the sales country, model year, and so on. Second group, development target group that contains system code such as model code, project code, and so on. Third group, test target group that contains information of unit under test, such as the prototype number, parts number, and so on. Fourth group, test plan group that contains test information, such as test name, test type, and so on. Fifth group, functional requirement group. Sixth group, measurement group that contains the measurement data. Okay, these data were partially used depending on the department or group. In this data model, those data can be combined into one and linked to test data. Therefore, computers can understand the meaning. For example, the following context is well explained in this model. We are developing a 2020 model ABC vehicle for the United States. A prototype of the battery is created and a performance test is conducted. The functional requirement number is 123. It can also represent system relationships. We develop powertrain for EV. Project code is ABC. And powertrain model code is AAA. The model code of the motor, which is a subsystem, is XYZ. The model code of the battery, which is a subsystem, is HIJ. And the prototype hardware number used in the battery test is 345, and the software number is 678. In this way, the world of engineering can be properly mapped into the digital space. Engineers can be connected to each other through these data models. For example, hardware designers can search for test data by parts number. You can also understand which vehicle uses this part. Software designers can search for test data by software number. Business strategy engineers can see data for many vehicles from the project code. You can also see the data at different system levels. You can see vehicle performance data at the system level, or you can see powertrain data at the subsystem level. You can also see component level data. In this way, engineers can quickly find and understand the data they need for development. In other words, engineers can use companies' important assets which are hidden until now. In fact, this model has another important secret. That engineering knowledge in the engineer's brain can be stored as a graph data model. Engineers create new data every day based on some data. A simple example would be to use engine data to simulate the output of a vehicle. Another example, we use data from multiple subsystems to calculate the performance of the powertrain. The same applies to trend data. We create data by gathering many past test data. Machine learning dataset is also same. These are described as a relationship between such input data and output data. It should be noted that the knowledge in the engineer's brain is stored as relation data. This kind of engineering knowledge can be stored at different levels, from vehicle level as system to subsystem level such as batteries. And this knowledge data can be used for many purposes. With reasoning, machine may be able to recommend what they want to do next. It may be possible to lower the skill set required for work and create a sustainable environment where many people can work. Also, the efficiency of frequent tasks can be improved by automation. What's more, relation of behavior data is used for systems engineering. So, engineering knowledge is relational data with great potential. We also use the graph database as the core of our system integration. This is an example of architecture. Neo4j integrate many databases. For example, a development DB that stores development information such as model code, a prototype BOM that stores prototype data, a test database for each group, and a file server that stores documents. The stored data can be sent to AI and analysis tool through the API. Of course, we also developed a GUI for human users. Let me introduce the application briefly. From this screen, you can see a list of development information linked to the test data. This is test plan information. It contains planner's name, test plan name, and so on. Project information contains information such as project ID, model code, and model year. Going down, you'll find platform design information, powertrain system information, engine subsystems, equipment, prototypes, functional groups, and more. You can also see other data, such as lower-level subsystems. This data came from the in-house database. Engineers can easily find data because test data is linked with many development information. Next, I will show you the function of linking with BOM. You can link parts used in test from this screen. Now select the hardware UUT. Press the T-BOM button to get the data from BOM. Select the parts you want to use in the test. By pressing Save, the parts were linked to the test. In this way, the BOM and test database are linked. I will show you the function to display test data. At first, the main information will appear like this screen. So select the test data you want to see. At the top of this screen, some development information is displayed. This is vehicle speed data. This is the ignition data. This is the intake temperature data. In this way, time series data and XY data can be displayed, and engineers can easily understand data. Next is automatic analysis and the engineering knowledge creation feature. This feature allows you to automate your analysis tasks. At the same time, the relation between input data and output data can be saved in a graph database as an engineering knowledge. First, select the input data you want to use for analysis. Select from the data number or data name. Here, I selected the data called fleet data. Next, select the data name and data number as the output of the analysis. Then select analysis type. Here you can see a list of analysis type which you register in advance. Each analysis has a Python program on the backend. This time, select Analysis 1 and run the job. Then, the analysis job is executed and the analysis screen will be displayed like this. Now complete the analysis and output data is stored in the database. In the graph database, the input data and output data are linked and registered as engineering knowledge. This feature can provide data from graph database to Python program by GUI. You can register any analysis. Also this time I showed GUI, but you can get the data by API also. Furthermore, as you can see in this page, multiple servers can be used for distributed processing. This is a combination of a graph database and Spark. Big data analysis can be processed at high speed. For example, deep learning and processing of huge data. Finally, I'd like to introduce the very important functions. This is automatic test data import function. This is GUI for some setting. On the left side, you can see folder structure. This feature can monitor folders on the file server and automatically import files into the database. In other words, it is IoT of test data. Engineers can simply save the file to file server and it will be automatically stored in the database. So engineers can easily store data into the database. Data import task is very tiring for engineers. Without this kind of feature to help data import, data is not stored. This is a very useful feature. In this way, we have been working with our vehicle development customer to create the product. The product introduced today is Bricks PVM. It is a unique product that was made with deep thinking together with the vehicle development customer. If you would like to know more, please feel free to contact us. Let me introduce reference materials. We have documents about this project. A document to explain data model is uploaded to the homepage. If you are interested, please download this document from our homepage. There are brochures, seminar videos, and white paper on the homepage. So if you are interested, please take a look. Okay, the seminar ends here. Thank you very much for watching.
iASYS. Connected research and engineering with connected data.